Today we're going to talk about performance measurement, and these things, I'm saying it's for APL64. For the by and large, what you'll see today is applicable to APL+Win as well. So if you're looking for comparative algorithms there, and actually the workspace I'll be showing you is an APL64, an APL32 based workspace, a W3 workspace that can be loaded in either context. And that's simply so that you can compare algorithmic things across those with a great deal of ease. And so let's go into here. So today, oh, this is great. So this doesn't want to, I don't know why I'm having trouble here. All right. Well, it looks like when I put the laser pointer on, it screwed things up so that my stuff doesn't work. Oh, so what I'm going to be talking about today is a workspace called the bench workspace. Contains two functions for execution time, and the ext function and the run function. And we'll look at the internals of the ext function, and in doing so, we'll focus on two particular things, which is the use of the quad TT and quad TF system functions for collecting and assessing timing information. And we'll also look at being sure that when you build timing algorithms, that you are measuring the cost of what you're actually interested in timing rather than the overhead of collecting the timing info. And it's a common mistake to use techniques that end up skewing your results because your timing over the collecting of the information skews your results. And the ext function is particularly focused on trying to avoid those couple of pitfalls that I've seen a lot of times. We'll also talk about the run function and how it works, and we'll talk about the run function is useful for assessing performance over a variety of argument sizes and so forth. And that very nice tabular format it presents, but it also makes itself very amenable to showing it pasting the results into an Excel spreadsheet and then building an Excel chart to compare algorithms with another. And I'll show you an explicit example of how to do that. It's pretty straightforward. The quad MF function, the monitoring function, the performance monitoring function, works basically the same in APL64 as it did in APL+Win, but it has some additional information that wasn't available in APL+Win, and we'll talk about those differences between the two. And I'll also get into using of the quad IR, which is an internal representation. In particular, I'm doing that so as to demonstrate definitively the impact on performance that the check system command and the debug system command can have on your execution. So we'll look into those factors. The bench workspace contains just two functions, ext and run. Ext measures how long it takes to execute an expression, and run does the same thing with an added thing that each time it calls your expression, it has a count variable, which is capital N, is the letter for number of that varies over a gradient of sizes, from one element up to 100,000 elements. And you can easily hack this to change this if you want a different distribution, but this I have found is a very useful distribution for it. So it basically is the same as the execution timer, but doing the execution timer again and again for different argument sizes. It's got a couple of predefined arguments that make it easy to work with integers or floats or Boolean data. Any other data you want, there's a mechanism for initializing that without counting that in your timing overhead, and we'll get into that. So let's look at the ext function. And in both cases, on the left is APL64, and on the right is APL+Win. And we're timing the expression that is in quotes, ext there, and we're looking at this iota 100 outer product multiplication of iota 100. So we're looking at how long does that take, and and we actually take, when we use this, we run the test expression many times, hundreds of times, but and then we do that in sets of that. So we'll run it multiple times, and then we repeat that test. And what we produce in the result is the mean and standard deviation of those runs. So the first element on line 87 here is the mean time that it took to execute the expression. This is not the overall time to do all those repetitions. This is factored into executing that expression one time, and it's displayed in milliseconds. So this took 0.02 milliseconds to execute this expression in APL64, and it took close to 0.036 milliseconds to do it in APL+Win. And then I just typically, when I run these, I run them at least 3 times, because there's statistical variation. Even though we're running the calculations many times, it's still good to get several samples of these. And so unless you're dealing with something that takes, minutes to run, you want to do this. And I want to do a little sidebar here. If you're timing your overall application performance, obviously you don't want to run it through this kind of a thing, because this thing executes many, many times. If your application takes 30 seconds to do that, you don't want to repeat that 1,000 times in order to refine your timing. That's not a good way of doing that. You just want to do your timing for your start of your application, and you can use quad TT to collect the timing information on a high resolution timer is a simple low overhead way of doing that. And we'll talk about that a little bit later. So there's a couple of variations of the ext function I'll show you. The first is this one with simple expression. You just ext and then the expression to be executed is the right argument. There's also, you can use on the left argument, repeat counts. It turns out that by default, the repeat counts are 2 things. The first element of the count is what are called their inner and outer repetitions. So we're going to repeat this expression many times. What this is asking us to do is, the first element is how many times do we repeat this expression, and we run it, in this case, 1,000 times, and then we collect the timing information it took to execute that for 1,000 times. We do that to get to fine tune the measurement, so that we're not taking the time after each and every time we execute this expression, because there's rounding error or there's sampling errors in the timer. The timer has some number of nanoseconds between the clock tick rate, and if you've got a very fast expression and you execute just one time and measure the time that results is not a very accurate timing for it. So this first element is, how many times do I want to repeat the expression? That I will take a sample for how long that took. I'll then divide it by this number, so that the time per expression would be whatever time it takes to run the expression 1,000 times divided by 1,000. That tells me how long that expression took to execute. The second element says, how many times do I want to repeat that group of 1,000? So this expression here is saying I want to do 1,000 iterations and collect the timing for that. Factor that to divide it by the count, and get how long did it take me to execute this expression per expression. And then I'm going to repeat that some number of times, and it's that I'm going to get the mean and standard deviation of, because I'm going to get 100 data points of how long it took, and I'm going to compute the mean and the standard deviation for those, and that's what we then return. Turns out the default, if you don't use the left argument, is 100 repetitions is the sample size that we use for repeating, and we do that 10 times. So the default arguments are 110. You'll see that when we look at the code. But that's the basic thing. There's also a variant of this where the right argument can contain what I call a prefix expression. And the notation is, there's a pair of colons that are used to separate the expression on the right, so if you look at line 93, the first part of it says A is assigned iota 100. And then there's a diamond that says B is assigned iota 100. And then I'm going to see the double colon, and the stuff to the right is what I'm interested in timing. I'm not interested in timing how long does it take to do iota 100? How long does it take to do iota 100 again to assign to B and then do this operation? Now, if that's what I want to measure, that's all fine and good. But in my case, the focus here is to say, how long does the outer product take to execute? So I don't want to have my test argument generation overhead be counted as part of the timing. I just want to do that. And that's what this double colon does. If you use the double colon, everything to the right of it is, you can have multiple diamonds in this to have multiple part statements, but it's that everything to the right that is part of the timed execution test. And everything that's to the left of it is the setup, basically. So there's the prefix expression that is the setup before the timing, and then we do the timing like this. This becomes very important when we get to the run function, because the run function generates an argument that is a count argument, and you might use those to build the arguments that you're going to use for your test that are appropriate for your test, and then pass those in, and that time the expression for those progression of arguments. So let's take a look at the run function that does just that. So the run function looks very much like the ext function, and in fact the left argument is exactly the same. The numeric counts works the same for the run function as it does to the ext function, except it applies to each of the successive set of tests that get done. And again, you'll notice on line 151 at the top there, you'll notice the double colons that are there. The test expression is L times R that we're interested in timing. But the setup expression to the left of the double colons is L is equal to iota n, and then R is equal to iota n. So n is automatically varied by the run function. This one variable is set each time to a different count, and the count are these values you see in the results in the third column of the results: 1, 2, 5, 7, 10, 25, 50, 75, 100, blah, 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 as we go down. So this is a nice distribution, a progression of sizes from very small, one element, up to 100,000 elements. And I have found it to be extremely useful to get some assessment, because different things run at different rates, and there are factors that affect. There's in arguments that are small, the cost of execution is dominated by the setup overhead of the algorithm internal to APL. And when you get into large argument sizes, it's the per element count that starts to dominate how long it takes. And this is a nice little example, which we'll look at in a Excel chart later in the presentation. But you'll be able to see how wildly divergent these kinds of things are from one another. It's easy to see that. And there also are predefined arguments. So I mentioned that there is the argument n that varies through these counts like this. It also are three variables, I, F, and B, that are an integer array, a floating point array, and a Boolean array. And they are, each time the run function works, in addition to incrementing the n argument, it also creates I, F, and B as vectors containing n elements. The I contains n integers, the F contains n floating points, and the B contains n instances of Boolean 1 and 0 values. So I, F, and B can be used as arguments in a test expression directly. So in this case, I'm looking at I times I. How long does that take to run? And I get a count that's down here, but it didn't have to pre-compute I is equal to n. I didn't have to do something like I is equal to iota n. I could do that, but I don't need to for those three special variables. And it's just those handful of variables that we predefine. And if you need a character variable, you can do it. You could say C is assigned n reshape of some character thing and then use it in a test. And we actually will demonstrate that specific case later. So let's, and here's just another one here, which mixed, it's two, the integer variables. This is the integer and the floating point variable together that we're seeing with the predefined arguments. So let's take a look at how the ext function is structured. And the key things to note is this is pretty standard in utility functions. Ext name itself is just simple function name. Everything else, all the local variables that are used in here are all prefixed with a double a delta underscore, just to avoid name shadowing issues. So if you're running this, if you copy these into your own workspace and run them, you can do so without worrying about name conflicts with variables that you might have. Of course, unless you have a bunch of double delta underscore prefixed characters that need to be seen globally. But this generally stays out of trouble for most cases. So repeated in here are the three the left and the right arguments. The left argument can be omitted, in which case it defaults to the values 100, 10, and 1. I didn't talk about that last argument yet, but we're calling the inner repetition count, the outer repetition count, and the init count. The init count can be 1 or 0. We'll look at that in a moment here. So let's keep in mind that there's a third argument, this init argument, that defaults to 1, and we'll look at how it's used momentarily. Then the expression is just an APL expression to be timed, optionally with a double colon in it, and the text before it is executed once outside of the timing loop, and the expression to the right of it is the actual expression to be evaluated for timing, and that one is what we time. So we parse the right argument here. If it doesn't contain any colons, then it's already properly formed, and the EXPR variable, delta EXPR, is already defined as the test expression. If that's not what we want, we're going to take everything to the left of the double colon and we're going to execute it. Down on line 16, we execute that whatever was to the left of it. So that initialization is done once and we're outside before we do any timing at all. We do that, but we've reset EXPR to be just the stuff that's to the right of it on the expression. So now we're set up for our timing to go. Now we're going to parse the left argument. In the left argument down on line 20, we just use the vget function to say I want the value of delta rep, but if it's not defined, so if we call this monadically, I'm going to make the default equal to an empty vector zilda. So I assign that to rep, and then I get the defaults for the inner, outer, and init values, and those defaults are 100, 10, and 1. A very simple common APL expression. Won't go into that. And I want to look then at the next part of the function. So the function is too long to display on one screen, so I've broken it up to about 4 parts. The next part of the function that follows the parsing the arguments is defining a local function, delta extr. I'm just going to say delta and not delta underscore. It's a mouthful enough. Delta extr is the timing function. We basically create an APL function that we're going to call that is going to do the timings, and this is the code that builds that. On the next slide, I actually show you a copy of what that looks like. So don't worry about this. It's just very straightforward call. But that argument inner that we use, the inner loop count, is used to create the timing expression repeated that many times. So by default, it's 100. We're going to do 100 reshape of the end close of this expression. And I use the notation prefixed with a colon space. That's this. You could also have used a monadic assignment arrow, which is the expression to just discard the result. The key point of either of these constructs is that and this colon one at one point in time executed a little faster than the niladic assignment arrow, which is why I prefer to use it. it also syntactically stands out more, and you'll see that in a moment. So here's the function that gets generated. When I call it here on the bottom in the session, I called 5 as the left argument to do this expression, iota 100 outer product times of iota 100. And I used 5 as the inner repeat count. The function it generated looks like this. On line 1, it samples the start time. And then on lines 2 through 6, it repeats the expression, the inner count times. And since I used the inner count of 5, we see 5 repetitions of the expression. And the last line takes and says what was the end time, and then what we're doing is there's a variable that got initialized to delta delta t is a vector, and we're going to add to it the next sample. So how long did it take to execute that? What I want to point out about the way I've constructed this is important in terms of getting the most possible accuracy out of your timing. Two things. A lot of timing code I've seen users build will do ostensibly what I'm doing here, except they'll use a for loop to repeat the test expression multiple times. But when you do that, you're including the overhead of the for loop as part of your timing that you're timing. So between your snaps of the start time and the end time, if you use a for loop to do the repeats of your expression, the overhead of executing the for loop is part of what you're measuring. And if what you want to measure is how fast is a for loop, by all means do that. But if what you really want to do is look at a core piece of algorithmic code and say, is this a better way or is that a better way to code this? And we'll look at a specific example of that later in the presentation. But if you do that, you're going to skew your results. So what we do instead in this function is we take the test expression and replicate it the number of times we're going to repeat it. This is an unrolled for loop. Instead of the overhead of a for loop, we just do the expression that many times. And on line 7, there's a very particular way that I'm getting the end time. A lot of times people will code using either quad AI or they'll use quad TT to measure. The quad TT is a higher resolution timer and it has lower overhead to sample it. And I highly advocate when you're doing timings, you use quad TT to sample the times. And so, but you'll notice a lot of times people would phrase this as in parens quad TT minus my start time. But I don't do it that way. I instead take my start time and I subtract my quad TT, which gives me a negative number, but then I make it negative. Why do I do this? I do this because I don't want any of the execution overhead of getting the initial value and before I get the TT by doing it, because APL, unless interrupted by parens and such, executes from right to left. Quad TT sample is the very first thing that executes on line 7 before we get the value of delta delta S. And that is a more accurate measurement. There's a little bit of loss here because, you know, it's not perfect. We have the overhead of assigning this statement is part of the timed overhead. And the overhead of fetching the TT value is part of the timed overhead here. But this is as accurate as I can do it. And by using it this way, instead of saying quad TT minus delta delta S for my time, I do it this way and then make this negative so my timing is as accurate as possible. Okay, so the next part is to actually execute the code. Now, so this was what the timing function looked like that we built for it. How does the execution happen in the ext function? Well, we do by default, remember that init argument which defaults to 1. Before we start our actual timing, we execute the ext function once to initialize. There's an APL has an overhead. This is true with APL+Win and APL64. The very first time you execute any line of code in a function, we have to pre-compile that code. Subsequently, that code has been compiled into what are called execution codes or X codes. And we don't have that parsing overhead to encounter on subsequent executions. But the very first time we execute a line of code, we do have that added overhead. In general, I don't want to count that as part of my timing. I want to count how long did the algorithm take to execute. Now, there's a place for measuring the compilation time for a line, and you will encounter that in your functions that are in your application. The first time they execute, they have an execution over a parsing overhead there, and there's no real way to get rid of that. But if you're doing comparisons of various algorithms one with another, generally you don't want to include that overhead as part of your timing. So by default, we build the execution timing function, this one that I just showed you. We build this ext function, and then we run it once to dispose of the parsing overhead. By default, we do that. If the third argument on the left is a 0, we don't do that. And then we will include that in our timing overhead. But by default, we do that once to remove the timing overhead. Then we do the actual timing run, and we repeat this the delta delta outer times. So by default, that's equal to 10. So we do 10 iterations of calling ext. Each time we call ext, I'm going to roll back the slide one more time. We're appending to the end of the delta delta t vector the time that it took to do these executions. And so what we're doing is we start out with delta delta t being an empty vector, and each time we run it, we append a new element to it. So when we're done with this, if we've done it 10 times, we'll have a 10 element vector with our 10 sample times of how long did it take. So then the next thing that we do in the function, and this is just to show, this one just shows the with and without the initialization calls. So the left argument on the left, we're doing one iteration and one iteration and including the but excluding the initialization overhead, and we see how long it took. Down below, we're doing 100 inner iterations, 10 outer iterations, and we're excluding the initialization overhead. So we see that. If you look on the right, the last element is a 0 here, and these include, and you'll see there's a substantial cost to doing that first part compared to what's on the left, the right and the left here. So that's what this is trying to demonstrate. All right, okay. So finally in the function, the last part of the function, after we've collected our timings in the delta delta t vector, we're going to actually scale those time units, because those time units are in quad TT tick units. These are timer ticks. Quad TT stands for timer tick. It measures the tick count at the beginning and the end of the function, and then we divide it by quad TF. TF is the number of ticks per second. It's a large number. It's about well, I don't remember what the number is. It's a large number. And we divide the timing ticks to get, this is the number of seconds that it took. So first of all, we divided the inner count into how long it took. That's the tick count per expression. So this is the actual cost of one iteration of the expression. Then we get how many seconds did it take per expression, and then we scale that to milliseconds. So we've now got t is a vector of millisecond times per expression, repeated outer times, the outer loop count. And then we're going to compute the mean and standard deviation, assuming that the count is greater than 1. If it's less than 1, then the standard deviation is 0, and we just report our time. So we return that in the else clause on line 53. Otherwise, we compute the mean and standard deviation and return that. Okay, so the run function is pretty simple. The idea behind it is it's going to repeatedly execute the ext function, but it's going to do so on it. Now it's a little more complicated, and so it's got a couple of utility functions in it. And rather than polluting the workspace, I just wanted two functions in the workspace. I want the ext and the run function. So the run function defines two functions internally. These are named delta delta head and delta delta out, and it calls those. But it defines them, and the way it does it, we'll see in a second. This first line of code on line 9 and 10 is actually obtaining those definitions. They're set off in some some special comment blocks below, and we define the local functions first thing we do. Then we parse the left argument. We're actually going to pass this through. The left argument is exactly the same as it was for the ext function, and the right argument is the same as it was for the ext function. So though we're going to pass the left argument through here, we just simply set the delta delta rep equal to whatever the argument was, or default it to an empty vector. And then we call the head function, the local function we defined locally, and this displays a little header display of the data. The next part of the code is we set up an execution counts. So this is where we get that progression that goes 1, 2, 5, 7, 10, 25, 50, 75, 100, and so forth. We simply produce that set of counts right here for our value of n. All right, and then we're going to iterate in this for loop, and we define our 3 standard arguments. Notice that n here was the progression, the vector of all counts, and we're going to do a for loop so that now inside of the loop n is going to be progressively 1, 2, 5, 7, 10, etc. And first thing we do inside of this is we define these 3 standard arguments. B is equal to simply n reshape 1, 0. We created a Boolean vector of length n. Then we create an integer vector of length n, and we create a floating point vector of length n here. So we've just got those standard arguments. If you need more specific arguments, you can define them in the expression using the prefix expression. Then we execute extr here to get the mean and standard deviation for executing our expression. And then we display those, and we format these to 5 decimal significant digits for our our expression of our mean, and our standard deviation and the count is displayed here. And then our local functions. Remember up here, we looked through the entire function. We got the quad CR of the function, and we looked for lines that begin with a comment followed by 2 dels followed by a comment. Well, that's what's at the end of the function, our local function. So I've simply embedded these. Now, if I wanted this to run only in APL64, I would have used the :def construct to create local functions. But since I wanted it to run in APL+Win also, I instead used this little more abstract way, or a little less efficient way of doing it with these locally defined functions. But it's a simple way of piggybacking local functions inside of this other function so that it stands alone. All right, so when we run this here, I'm going to compare 2 algorithms. On the left, I'm using a new quad FL. This is find last. I'm looking for occurrences of ABC in a character vector C. And then I'm getting the first element of that. That's the index of the last occurrence of the vector ABC in the argument. And the argument is equal to n reshape of ABC. So I'm just repeating ABC many times, n, which is our argument size count. So we do that, and that's what we execute. On the right, I'm executing a different algorithm that gets the same result, which I'm using quad SS to find all occurrences of ABC, but then I use the quad where function to find the indexes of them, and I'm taking the last occurrence of the index. There's plenty of other ways you could code this, but this is just one alternative manner of doing it. When the run function executes, it first line, this is what's displayed by that little head function, is it puts the sys version information out here. So it writes out the version number, the date of the build, and it labels it as APL64. If you were running an APL+Win, it would do the same thing, but it would put APL+Win at the end of here. So it makes it easy to see what your results are. It also displays what is the algorithm that you're timing, and it breaks it in. If there's a prefix expression, it breaks it into 2 lines. So this is the prefix execution. This is what's actually being timed. And then we see all of our outputs for the different sizes. So we can display this easily. So I've taken these results and I pasted them into an Excel chart here, and into an Excel spreadsheet, and then used a chart. And I'm going to show you how I built that. It's very straightforward if you're not very familiar with that. And this output format, it makes it very simple to do that. So here we're going to go to the next item, and you can see, let me go back here. So let me give you a slight prefix, a pre of this. So what I'm going to end up doing here is I'm going to paste the two sets of expressions into successive sets of columns. I'm going to then create a chart, and I'm going to select the items from this chart for graphing. So that's what you're going to see. So I've run the thing already, and I take that, I select it, I tab over to my Excel spreadsheet, and I paste that in. I get ready to paste the next one. We go back, I scroll to where that is. I gather that information, and I'm now going to paste that into the Excel spreadsheet, and we paste that there. And now I'm going to create a chart. So by that, I'll go to the Insert menu in Excel, and I'll select, I want a line chart, and I'll select a style of a line chart that I want, and then I'll select the data that goes into it. I select one column. I continue to hold the control key down while I select a second column. That creates a second time series. So I've got two time series, and then I edit what my labels are. The labels are the number of elements in the result. So we've got that, and that generates my chart. That's all there is to it. If I had multiple time series done, or I might have had APL+64 in one of these times and APL+Win on the other one, if I want to look at relative comparisons, I can do that. And having a graphic display like this is way nicer to look at and meaningful to understand the algorithmic thing. So you'll see that they're pretty comparable in performance. APL+Win is a little faster in this particular case in small argument cases, but really takes off. The red line is the quad SS quad where algorithm, and the right line is the blue line is the quad FL algorithm, and that's clearly the winner here for what's being asked to do. So that's pretty straightforward. Let's talk about quad MF differences. So in quad MF, we have, in APL64, we have a 5-column result instead of a 3-column result. And in the 5-column result, we have 2 new columns. And these tell us how long was, the 4th column tells us how long was spent parsing of this line. So how much of the execution time was due to parsing as opposed to actually calculating something. And the 5th element is how many times did we parse this line? It's actually possible. Normally, a line will only be parsed once in the life of a function, but it's possible under special circumstances, and we'll get to those, that a line might be parsed multiple times. So if we look at this, here's 2 simple examples where I create a function on the left and on the right, and then I display the quad MF times, and you can see the difference of the 5 columns on the left and the 3 columns on the right. You'll notice too that there's a scaling that needs to be done, because the quad MF returns in its raw form returns in columns 1 and 2, and in the case of APL64 in column 4 also. It returns timing information in terms of tick counts, and those aren't in seconds, and we have to scale them to be in seconds. And so if in seconds, or actually, I'm sorry, in milliseconds. And that is done, you can call quad MF with a -1 argument, and it will return the scaling factor. This is this value is the number of milliseconds per timer tick is what this returns. So by multiplying those columns of the result by that, I'm basically scaling those values into milliseconds. And so we see that the overall time for the function was this, and the bulk of the time was here, where we're executing this over and over again. And over on the right-hand side, we see the same thing. So that's really the difference between them. I'm going to look really quickly, and we're wrapping up here. We're going to look at quad IR. Quad IR, and I'm using this to demonstrate we're going to get to 2 commands that can affect your performance. Those are called the system commands, check and debug. And I want to show you quad IR as a graphic illustration of how those do it. But let's just dig into quad IR a little bit. When you use quad IR on a function, quad IR is APL64. In APL+Win, it's a quad IT function, and the name of that sub function is called IR. it stands for internal representation. And this gives a layout of the function with some internal representation. Now I broken it into two parts here because it's too tall to fit on one screen. So on the top is APL64. It's a little different format, but it shows basically the source code and all information about that. The real interesting part are where it shows what are called the X codes. This is the next page of the output here. And in APL64, it shows us what those are. Well, now we're actually in a function that we had QuadMF monitoring on. And so what you can actually see is up here, there's a X code on line 1 in the left on APL+Win. There's called XMON line. It's an extra X code that gets inserted when we execute the code. And this is the start of monitoring for that line. And it snaps the timer for this line of code. So one of the things I'm trying to demonstrate here is that when you use monitoring, you're going to slow down the function because you've got to capture execution times, and it's done literally with an execution code called monline. And then you have the rest of the X codes that execute that function. And I'm not going to go deeply into it. I will say it's a lot easier to read in APL64 because it gives them, each X code is explained in a brief term what it is that it's doing, and it shows the arguments, and much less cryptic than in APL+Win. So it's a nice display of that. When monitoring is removed, those codes like here, there was the mon line that I showed you there. When I remove the monitoring, so I turn monitoring off and then I display again, those monitoring codes have disappeared. So they no longer have an overhead. So make sure when you're doing any timing tests that you don't have any residual QuadMFs in there for either running your app or for that. You want to get rid of those, and you want to do that either by using QuadMF with a 0 argument for all the functions that you want to turn monitoring off on, or you can redefine your functions like QuadDef, QuadVR of each instance of your functions will also dispose of all the monitoring information. Anyway, that's just to illustrate that. Now I want to talk about the check command. What is the check command? This doesn't exist in APL+Win, but what happens is every time you can either enable, the check command allows you to enable or disable the checking of the valence of all names used in a statement before each execution of that statement. This is really important. And it almost never is necessary. And I'll show you a case where it is. Valence checking means that the assumptions that were made when we compiled that line previously are still valid. Variables that were used in that line are still variables, and monadic functions are still monadic, and dyadic functions are still dyadic functions. If that has changed because you edited something or erased and redefined something and you try to execute it, we will have built X codes that are trying to execute the statement in one meaning, and we will get an error, and we actually get a thing called a type error. If we try to use what we thought was a variable, but it's been changed from a variable to a function, we will get a type error normally because that has changed. If you're willing to pay the extra execution overhead to check every single time before you execute, and for development purposes, this is a great idea. You just got to remember to turn it off in production. So the check command allows you to enable or disable this valence checking. And if it finds that the valence of any of the names that are used on the statement have changed before it tries to run the statement, it recompiles that line. And that way you don't get these type errors that would come off. It is off by default in a clear workspace. It does slow down execution slightly because if we're going to have to check all those names before we execute the line, there's a certain small overhead to doing that. And it is saved with the workspace. So once you've defined the check state on or off and you save a workspace, that state is saved with that workspace. So you can save a workspace with checked off to be the workspace you're going to use when you run your application in production. But when you're doing development work, you probably want to have check on. It'll slow things down ever so slightly. Remember, if you're doing timings, that you turn it off because it's going to skew the timings a little bit to have that check function in there. Let's look at this in the X code, what this looks like. So remember, I had this foo function over here, which does assigns a value to k. It then does a for loop iterating through these. It does k times k, and an end for statement is done. And when I've turned the check was off, I turn check on, and when it does what's called reflowing the functions. Reflowing means that it's going to rebuild all of the functions in the workspace, either in the checked state or the not checked state. And it throws away all of the previously executed and compiled code. Remember, when we showed this code before, we had all these X codes that had been done because we executed it. After I clear the state, we've thrown away all the X codes, except for a couple. It turns out end for statements and a few other statements get pre-compiled and baked in at the time of function definition. Don't worry about why, but that's the truth. So right now we look like this, and we're going to execute the function once. So I'm going to execute foo once, and then I'm going to look at the internal representation. You'll notice on each line, each statement, there is an X, most statements. If there's any variables or functions used in that statement, there's an X check statement, which will check that the valence hasn't changed. So it's expecting k to be a variable before it executes this line. If it's not, it's going to recompile the line. All of these are done. Let's go to a little different example. I'm going to create a variable called mystery. I'm going to define a function foo that has one statement in it that says mystery iota 10. And I define function foo and execute it, and guess what? It sees mystery as a variable, so this iota is a dyadic iota, and it's going to look up the value of 10 in it. It's not going to find any occurrences, but since mystery is 7 characters long, it's going to return 8. So foo displays a value of 8. Let's look at the X code that got generated for that line of function. It does a check on this, and then it generates this code, which is fetch the value of the variable mystery, apply dyadic iota to it, and then that's the end of the statement. Let's display the output. Well, let's change this different. I'm going to erase mystery. I'm going to define the function exactly the same way, and then I'm going to execute it, and hang on a second. I've defined the function here to simply display whatever the argument is. So when I execute foo now, instead of displaying 8, which is what we got before, it displays iota 10 here. Why did that happen? It happened because the check just determined that check was originally back here said that it has to be a variable. Well, when I execute it this next time, it wasn't a variable, so it rebuilds the function, but now it's a monadic function. And it records that for the next time we execute it, but it builds it a little differently. Now it fetches the constant value 10, applies monadic iota instead of dyadic iota because it sees the context of it, and then it executes a user function monadically, which is the mystery function. So the mystery function gets called with the result of iota 10 and displays that. That's a big change. But what would happen if I turn check off? Well, if I turn check off and I run the function, it behaves just like it did there before, but you'll notice that the xcheck code is no longer being emitted in the output. So it executes these things, and it's an execution with a little less overhead because it doesn't have the check overhead. But what happens if I erase mystery and redefine it now back as a variable? When I run foo, I'm going to get a type check error because it expected mystery to be a monadic function and see the check function documentation for this. And that's here again is the function, what it looks like. And we got the error because when we tried to invoke the monadic function mystery, it's no longer a monadic function, and we get the type check error. Now, in production code, generally, you want the check state to be off because you don't want the overhead of checking. In development code, you generally want to have check on. But I will tell you that it's off by default. So this important thing to remember, in your workspaces, it's off by default. If you ever get a type check error, and you won't very often, but if you do, because you're changing what was a variable to be a function or vice versa, you might get those. And you can repress that and make it so that it automatically recompiles the code by having the check state on, but it is off by default. last thing to talk about is the debug command. And I'm going to talk about it because this can impact your timings if it's on, and it is on by default. So keep this in mind. It enables or disables debug statements such as :debug, :assert, :if debug. Those statements are either on or off. It's on by default. It will slow down execution when it is enabled, but it only slows down execution to the extent that you've coded debug, assert, or if debug type statements in your code. And it is saved with the workspace. So let's take a quick look at this. I've defined a function here that what you can see here is it simply displays foo was called, then it does an assert when debug is on of the argument is equal to 1, and then it will do a debug and display iota 10. Well, we got stopped right here at the assert because when I called it here with an argument of 1, it said foo was called and then it displays iota 10. But when I call it with foo equals 0 on line 9, it says foo was called, but then it gets an assertion failure on line 12 because I've asserted, and this assertion is only evaluated in debug, and when the debug flag is on, I've asserted that the argument is equal to 1, and it fails. If I look at the Xcode for this generated line, you can see that there are line 1 is generated it's a normal line, but this one, which is assert, is generated with a control statement, an XCS debug statement, and the assert Xcode. And this next one of debug is generated similarly here. If we make one more change to that, and I reset, clear the SI stack, and I turn debug off, and then I run foo again, I run foo with 1, and it displays, and I run foo with 0, and I don't get an error this time. It don't get an error because because that debug statement doesn't get generated, does not execute when debug is off. And so if we look at the Xcode that gets generated for it, if I look at foo, you'll see that it's streamlined. And even though there is line 2 has an assert on it and line 3 has a debug, you'll notice that they didn't get generated. There is down here on line 35 in the display, we see line 1 is here, but following it, line 2 and 3, there's no trace of those lines. They have 0 overhead at all. The assert has disappeared and the debug statement has disappeared. If it was an if debug block, that block would have disappeared. It wouldn't have been compiled at all. And so that turns the code off. And if I now turn debug back on and execute foo again, you'll see that all of those have come back. So all of the assert statement and the debug statement is back. And that is it. So have at it with any questions you might have.